Okay, today we shall begin with what I say, the intense stuff. And I'm going to give you a scenario. I'm going to give you 2 minutes to struggle with it. And at the end of the 2 minutes, you'll still be struggling probably. But hopefully lesser. Okay? So what this scenario is that it's a ball sliding down a bigger sphere of radius r. And you agree that at some point of time, the ball will lose contact with the bigger sphere. Some point of time. Now, some people will think that it will lose contact over here. No, it will lose contact earlier. The question is when. Right? So, my task for you in the next 2 minutes is just to understand the question, think about the forces acting on the ball, think about how it relates to circular motion, because it's obviously circular motion before it leaves, before it goes into projectile motion. So, think about the forces, think about the motion, think about how those forces relate to circular centimeter force. So just give you 1-2 minutes, grapple with it. Consider the ball at the arbitrary position angle theta from the vertical. Think about the forces, think about how it relates to centimeter force, think about what other conservation laws can you apply. I'll give you 1-2 minutes. Think about it. Try to grapple with the situation. The ultimate task is to find the position, the angle where the object goes into action. That's the ultimate task. Okay. Think about the forces. Okay, repeat this again. I'm going to chart this. Think about the forces. Think about how they relate to centimeter force. Think about where the centimeter force points. Think about other conservation laws that hold true. One more minute left. It's a smooth surface. Smooth surface. So there's no rolling, it's only sliding. Alright, anyone would like to tell me what are the forces acting on the ball? It's on the smooth circular sphere. Weight, excellent. So weight over here, and what else? Normal contact force. Normal contact force is always normal to the surface, so it will point this way. But we're only interested in forces directed along the radial direction, because that's where the centripetal force is going to point. So therefore, if I resolve this force, we probably have pulled this weight out. Can you see that if I resolve it into two perpendicular components, if this is theta, I hope your math has been learned well, so you can see that this angle over here is theta, which is actually this angle over here. Cool. Therefore, can you see that this component over here is W cos theta? Okay. So therefore, can you see that by using what we learned about centripetal force, the centripetal force always points towards the center of the circle. Now tell me, is W cos theta bigger or N bigger? If W cos theta points here and N points here, and knowing that centripetal force must be directed towards the center of the circle, and it is a net force, which one do you think is bigger? Is this correct? Or is this correct? Which one is bigger? If N is bigger, do you agree that the net force will be pointing here? It's going to point away from the center of the circle. Right? So which one is bigger? I told you the answer already actually. Sorry? Sorry again?
Can
If they are equal, then there's no net force. Then there's no circular motion. But it is undergoing circular motion. Right? Yeah. So it must be W cos theta. Yes, right. This is correct. This is wrong. Why is it correct? Why is it wrong? Because the net force is pointing towards here. Okay? So it's a very modern idea. And it's consistent throughout all the examples I showed you. Net force points towards the center of the circle. Net force is centripetal force. And now this is the problem. We got W cos theta minus n equals mv squared upon r. Now we have to get the expression for n, which is equals to W cos theta minus mv squared upon r. And do you agree that the point where the object loses contact is the point where n becomes equals to what? What's the value that n must take when it loses contact? Zero. So then we got to struggle. How do we find theta? If we let this become 0, we still have this to grapple with. So which is something that is not expressed in terms of theta. Now this is the part where you need to use another conservation law. Now tell me what other things, is there something that's conserved? Is momentum conserved? Ask yourself, is there a net force acting on an object? Yes, there is. So momentum is not conserved. So other than momentum, there's something else that you learn that's conserved. You learn it in secondary school, secondary 3. Conservation of energy, exactly. So this is the part where you need a little bit of trigonometry. If this is theta, this is r. Can you see that the height loss is here? The height loss by the object is here. Can you therefore see that half mv squared is equals to mgh? And therefore, mgh is just r1 minus cos theta. Why? Because if this is r and this is r cos theta, then that will be r minus r cos theta. That will be the height loss. So you follow? You follow? Therefore, can you see that mv squared upon r is equals to 2mg1 minus cos theta? Just need to shift things around. Therefore, can you see that I can beautifully plug this in and get an expression in terms of theta for n? The v is now no longer in the equation. See that? So then it is up to you for you to find out what's the angle where it leaves off. I can make your life a little bit even more difficult by asking you to find the distance from the bottom where it goes into projectile motion speed. But that's to make your life too difficult. But I guess you get distance now. Go ahead and find the angle. I want you to find the angle. Come on.
Okay, so big R is the same as small r.
Big R same as small. Yeah. I just use it as interchangeably. Because the radius, this is the radius of the motion, this is the radius of the circle, so it's the same. Assuming that of course the thing, the small little ball over there is negligible radius. Otherwise it's very different. Hang on, it is still the same. Give it a try. Tell me what's the angle once you found it. cosine inverse 2/3.
How many minus 48?
48. 48. Don't know where the 4 comes from. Okay, from another equation. 48.
I thought we need mass.
No, you don't need mass. Mass you can solve. The m over here, you can solve with the m plus mg. The m over here can solve with the m. So in fact, the g also can solve. 48. 48 each of million. Now here comes the challenge question. For those of you who have sleepless nights, you may want to try this and see whether you can get the answer. The question is very simple, but the answer is not. Question is, what's the speed that I should project this inside a sphere of radius r, such that the ball goes here, lose contact over here, and passes through the center? What's the speed that I should project the object at the bottom of the sphere so that it goes up, loses contact, and goes into projectile motion, and then passes through the center? Don't do this now when you have sleepless nights. Yes, it does, of course, it does. Because right after this point, it goes into projectile. And it is not easy, it will be quite heavy on math. Some people will look at this and they fall asleep. It's okay, sleep is more important. Now, okay, coming back to planet Earth, is this okay? To understand the Unfortunately, I wish to tell you that there's one way to solve all kinds of circular motion. There's no way. All you have is conservation laws, concepts, principles, and that's all you have. How you can actually know when to use what, comes with experience. The more you do, the more experience you acquire. Then roughly you know what's the approach to use. I'll give you about 3 minutes more to assimilate this. And I'm going to give you the next one. And then we'll move on to verification. Probably one more question to walk down. Can we go? The mass? You cancel it over here. It's mg cos theta minus 2mg plus 2mg cos theta. When you set this to be equal to 0, the mg cancels off. When you set n to be 0, the mg cancels off. You can divide the whole thing by mg. So the mass, the g doesn't have on it. So which means that if you repeat this experiment on planet Moon, on Moon or on Mars, it will be the same answer. Which is interesting. It will be the same answer in Mars, Moon, Uranus, Jupiter, each other. Now we go on to challenge it. If you recall this, $5. Oh, whoa. The brightened eye is on $5 is too much or $500 is too little?
There's more.
$5
There's
only.
more of us.
Then 125 each?
Yeah.
Enough for a cup of water.
So what's the deadline?
Sorry? Before you graduate.
So I get
No, I wish to give the $5. What do you mean? What do you mean by I'm so confident that I won't give it up? Okay. Now I'm going to give you the next question, yeah? Ladies, you understand the question over there? You understand now? And then I will just go on. Okay, now, can you see that this scenario over here, I got a ball over here, this is L upon 2, this is L upon 2, and then this thing spins. Okay? Now what will happen to the bead if it is just threaded through the rod over here? So you got a rod, this bead over here is threaded through. So it's actually free to move along the rod. Now when the rod spins, what do you think will happen to the bead? will spin out, right? Yeah, it will be thrown out. Agree or not? If you're on the turntable or if you're on those kind of merry-go-round, I don't know whether you have childhood or not, or whether your childhood is stand you know playground, you know this thing called playground. In case you don't know what is playground. The playground is like wow, war zone, shooting people down, sniping people. Okay, if you go to the playground, I don't know whether you know this thing when you turn, you know.
So
Generation differences.
We had a childhood.
You had a childhood.
We didn't have one.
Yeah. If you start spinning around, you feel yourself getting thrown out. Yeah? You have to hold on to it before, otherwise you just get thrown out. So, this thing will be thrown out, but the question is, what's the force to which the object is going to be thrown out? This is where your favorite centrifugal force comes in. Yeah. Actually, it's not, I wouldn't call it centrifugal force, but the effect is as though, if there is nothing tying it over there, it's as though this object experiences the force throwing it outwards with mr omega squared. Yeah? So therefore, can you see that F equals to mr omega squared, which is ma equals to mr omega squared, and cancels off dv dt is equals to, or rather dr dt, because it's going to move in this direction. dr dt, vr meaning the velocity in this direction, is equals to r omega squared. So dvr equals to r omega squared dt.
Why is it that the ball is not at the centrifuge?
So again,
The force is
the force is what?
centrifuge, the formula for
Yeah, okay. The thing is that it's almost the same as the object. Okay, if you imagine you're sitting inside a car or a vehicle, and the vehicle travels with acceleration with constant speed v, and then it starts to slow down with decelerated a. Then you feel as though that you're moving relative to the vehicle at the acceleration a forward, when the vehicle is actually decelerating backwards. So it feels as though that something is pushing you forward with the force of ma. This is exactly what this is experiencing. Relative to the rod is actually, everything is trying to accelerate towards the center. So relative to points on the rod, it is accelerating backwards or outwards.
So it's like inertia.
Inertia, that's right. It is relative.
So can you repeat the question?
The question is, what's the velocity of the object when it reaches here? This one.
So it moves along.
Okay, so is it like the object will move along the
Yes, correct. The bead over there is actually threaded through the the rod. So it can actually move along the rod. So over here we have dvr dt equals to r omega squared. Actually, hang on. We should use this thing over here instead because it's r term over here. So it's dv dr times dr dt, which is dv dr times v equals to r omega squared. The reason why I decided to use this is because I realized that it's r over here, so I need to integrate it with respect to r. Therefore, I have v dv equals to r omega squared dr. If you integrate this from 0 to speed v from L on 2 to L, you'll be able to get an expression for v. Yeah, first thing, actually from here onwards to here, it is math. What I want to focus on is this portion here. Okay, now let's go back to the concept. Let's not talk about circular motion, let's talk about linear motion. If you're in a bus, and the bus is traveling at constant speed v, and the bus suddenly decelerates at acceleration a. So the bus is traveling in this direction and slowing down. What will happen to you? You'll be thrown forward, right? It's as though you're being thrown forward with what force? And I'm saying, it's as though someone's pulling you forward relative to the bus. Now this is exactly what the bead over here is experiencing. Now, all points over here, do you remember centripetal acceleration is actually towards the center of the circle? All points over here is trying to accelerate forward towards here, towards the left. So this bead over here will seem as though it experiences a force towards here, relative to the rod on the other side. Let me try to draw another diagram, yeah, so that you can understand better. So this ball over here, when it spins here, this ball will try to move in a straight line. Agree? Yeah, it try to move in a straight line. If it had spin together the rod, then it would have been here. So it moves from here to here because of the tendency of the ball to stay in a straight line. So So relative to the center of the circle, it is actually being pushed outwards. You get that? So if you perform the integration, you get the expression for the force. I didn't start from 0. Do you know why? You know why I cannot start from 0? If I start from 0, it won't move at all. Because it's 0. It won't even move at all. So it has to start from somewhere from 0. Oh, because it starts moving from here, so I released it from here. So the velocity over here, the velocity over here is not the velocity in this direction, it's the velocity in this direction.
I was thinking about that.
Still here. Then the rest is math, like what I was explaining earlier. This part is physics. Once you understand why MA is equal to this, then the rest is really just noodling through the integrals. By the way, people from the start of lesson till now is all ASD, so you must be very good at all this. Don't panic over things that you don't need to panic. Yeah, it is ASD. I'm still thinking of $5. Working really hard.
Not yet.
That question is not difficult conceptually, it is difficult mathematically. It's very difficult mathematically. So in short, it's like those kind of thing where you put a minus plus plus and you come out with the whole thing already.
Also, so it's like regular math.
It's regular math projectile motion. Depending on what you define as regular math.
You put one side and then you hold
No integration.
no integration.
I think it's something to do with like point, right? The distance traveled is radius r. So
The
and
horizontal.
then yeah, so like horizontal is
If I didn't offer the $5, I'd be brilliant. But since I'm offering $5, I'm going to be brilliant. All you can say is that you can learn everything again. Everything.
So
Yeah.
it's
Okay, people, can I move on?
this one is the velocity.
Can. Okay. For those of you who are okay with this question, I urge you to think about something, yeah? Is that force that as this turns around, is that force that this is being pushed, is the force that this experiences the only in this direction? Are there any other forces acting on this body other than the force that is the virtual force that tries to push this out? By the way, why I mention virtual is because it's actually the force that we are talking about, m omega square over here, appears because it's simply because of this ball trying to move in a straight line.
but it's cancelled out. The other forces are cancelled out because like it's the like gravity and
Okay. We're talking about horizontal plane now. Horizontal plane.
Oh, wait, this 90 degrees. Oh, this entire thing is not okay.
Yes, horizontal plane. The main thing is simple. There is a force 90 degrees. Now take a look. As I move the object, as the object moves from here to here, do you agree that the velocities are different?
Yeah.
V1, V2. Do you agree therefore that the object is actually accelerating in this direction as well? You can see the whole rod is moving the same omega. Remember that V is equal to R omega. This V is this V over here, not this V.
Oh.
Can you see that as the ball is being thrown outwards, it is forced to move with a larger V? It has to move with a larger V, which means that there must be a force pushing the object this way. Right? The object is actually moving faster and faster towards this direction as it is being thrown outwards. Therefore, for this to be possible, there must be a normal contact force pushing the ball this way. Okay? Agree now? Okay now? So agree now? Therefore, can you see that the dV, the change in the change in the V over here is equals to the small little changes times omega. I think I better write it the other way around so that it doesn't make it seem as though it's dr omega, it's omega dr. Okay. Now if I divide both sides by dt, then you see that this will be omega dr dt, which is actually equals to omega v. This v is the radial v. That means the v in this direction. Now this is exactly the same goes if you talk about Earth, and if you were to move towards here, can you see that as you move from the equator upwards, the horizontal speed over here is higher than the horizontal speed over here? Make sense? If you go up the latitude, the equator has a higher linear speed as compared to if you move up, the people over there actually move with a smaller linear speed. Make sense? So, to the people over here, you start drifting towards the right or left. You have a higher speed towards here. So as you move towards here, when people are moving with slower speed here, you tend towards the you tend towards the right. Let's give an example. We calculated if you move at 400 meters per second, you have 400 meters per second towards here. But the people over here only have 300 meters per second, for example.
Okay, so sorry, you're talking about the people floating in the air.
No, the people are grounded on the air, on the ground. If they are on the equator now, you are actually moving, say for example, I'm just giving fictitious figure. If you are on equator, you are moving at 400 meters per second due to the rotation of Earth, yeah? But if you go up the latitude, because you're describing a smaller circle, yeah, your radius is smaller, and because of the smaller radius, you actually move with a smaller linear speed. Right? So people over here has a smaller linear speed than you, who has 400 meters per second. They are moving, yeah, they're moving left, but we will tend to move towards the right relative to them.
That's when you
So-
drift from the equator north.
Yeah,
No,
when
in
you go
contact
north,
with
it's
the
right. When you go south, you go the other way.
Yeah.
But you're not in contact with the ground. It
Uh,
drifts that way.
Imagine that yeah, say for example a mass of air, say for example a mass of air that's moving from equator up.
Then, yeah.
Hot air moving from equator to the north.
So you're saying instantaneously, if you were like travel to that spot, you'll be flung like 100 meters per second.
Makes sense.
And that's if you have, imagine if you have huge mass of air moving from here to here. That's when the mass of air will start to drift towards the right relative to the people here because it has a higher linear speed when it was an equator. And that's why hurricane go this way in the northern hemisphere. And we talk about hurricane because we are talking about massive movement of air over large distances. And as you can see, the effect only comes into play if you have large distances. Seriously, come on, if you move towards the north from this point to the next part of the school, you don't drift lah. If you drift, it's probably a drunk. Right? I mean, you're talking about large distances. That's when the effect is obvious.
So
Yeah.
that's why you cannot teleport, right? If you teleport, then you
You can suddenly get thrown one side of them. You can teleport to other places in the, let's say, latitude.
Ocean left.
Latitude, yes.
Teleport up your own.
Once you teleport up north, you appear there, the ground will suddenly just. It's the same as you being thrown out from car.
so if you go
It's the same.
so like the change. What about airplanes? Like, what so
Airplanes.
like you fly from that point to
Uh-huh.
that point, so it's gradual.
It's a gradual thing. So it's over 13 hours, say for example. You don't feel it lah. But if you're talking about like say shooting cannon, shooting artillery fire, it does affect the effect. If you don't take into effect this force, if you shoot over a range of 450 kilometers, you miss the target by 100 to 200 meters. It's a huge effect.
This is you but change to 400.
Yep. To the right actually, relative to.
So how do you spell that?
Coriolis. It's an important thing if you talk about Coriolis. Coriolis. I think Coriolis. Not very sure about where the position of I is. Coriolis or Coriolis. I think it is. And the expression you'll find that is actually the acceleration, the Coriolis acceleration. There is actually a more complex mathematical form which involves cross product, which I have not learned. I shall spare you from that. But the magnitude, let's talk about just magnitude, is omega. Okay? So the appreciation of that, the forces involved. So you actually have a force this way throwing it out. You also have a force this way pushing it. Interesting things. The first evidence that the Earth is actually a rotating body, because in the past people believed that the sun, everything rotates on the Earth. So the first evidence that Earth was actually not a flat surface but a circular surface that rotates is this thing called, you can go and search it out, Fokker pendulum. Now the pendulum is actually a very simple idea. It's a pendulum that is swinging like this, usually very tall, very long, so that it has substantial velocity. And it is actually mounted on a plane that can be rotated, so it can actually rotate freely like this. So I'm not sure whether you can imagine. So the pendulum oscillates like this, but it is mounted, the whole thing is mounted on a turntable, so that if you want to turn it around, you can actually turn it in different planes. Yeah. So what this person discovered is that if you set up this pendulum and let it oscillate, because of this force over here, small effect, but if it is a long pendulum over a large distance, like 4 stories high, this force will actually cause the plane to start turning. And there's an equation that relates the rotation of that plane to the latitude of the system. Yeah, there is actually an equation. And that was the first evidence that the Earth is rotating, not that the sun is going round us. So flat Earth theory people will be very upset when you hear all this. Yeah. If we go Netflix, there's actually this documentary about people who believes on the theory that the Earth is flat. I don't know why they still believe in it, but
I have nine.
Ken, so are we okay with this? Shirley, is your head spinning already?
That's not the pendulum.
Okay, so
I don't understand the pendulum.
which one? Before you say everything.
The pendulum.
The pendulum. Oh, this one, focus pendulum.
Yeah.
It's okay. It's just meant to be something for you to go and research on. You don't need to, just go and find out more. The math is complex, but just understand the physics. Why is it that it turns and how is it related to the latitude? Just understand it. Don't be so anxious to try to understand everything.
So like, I don't understand how they want to see the direct connection.
Which one? This one and this one.
Yeah,
Okay, Ken. The idea over here is that because it is moving from this point to this point, it has different linear speed over here. And because it has different linear speed, there needs to be a force acting on it to push it so that it can move faster. Yeah. So if there's no such force, do you agree that this thing will be lagging behind? Yeah. So that idea of an object moving from this point on Earth to another point on Earth having different linear speed results in this object traveling towards the right because they have different linear speed. That's the concept. Yeah. The math of it is a little bit like this. At least the physics, the understanding. Why is there even a force? Ready? Okay, let's move on to the next part, which is the last advanced part I'm going to go through today, and that will lead on directly to gravitational field. Okay, I'm going to show you the exact, or more or less the similar way of how Newton came up with the idea that the gravitational force is 1 upon r squared, dependent on 1 upon r squared rather than 1 upon r cubed or 1 upon r. So I'm going to start off with something simple. This is almost an exact process of thinking. So let's transport ourselves 200 years back. Now, when you project something over here, slowly, it will actually come down like this. So this is planet Earth, this is a mountain. And if you project it fast enough, it will go into this. If you project it fast enough, then you see that it will. Yes, exactly. So if you fire a gun at about 7.6 km per second, and if assuming there's no air resistance, you'll be shooting yourself after 1 hour for 30 minutes later. It will come round and then hit you from the back. So, but there's air resistance, so no worries. So why is this important? Can you see that the circular motion mr omega squared, which is centripetal force which is required, must have been provided by the weight. Because the only force acting on an object is weight. And since the object is going through circular motion, this must be true. Okay? Okay, yeah? Okay, good. Now, therefore, this is r 2 pi upon t squared, which is 4 pi squared r upon t squared. You okay with that? Now, Newton knew that g has to be directly proportional to, inversely proportional to r, but he didn't know what n was. So what's the power to which it is reliant on? So he just let it be k upon r to the power of n. Yeah? So therefore, if you rearrange the equation, you'll find that t squared is proportional to r to the power of n plus 1. Okay? So okay, just rearranging the equations. Cross multiply. Now this is where the other scientist comes from. The other scientist called Kepler. He found from empirical evidence. That means he observed the stars, every one of them, and found, knowing the distance from here to the star, he actually realized that anything going around in orbital motion follows this. From empirical, that means empirical data, from making observation in the star. He drew all the stars that he observed, the distance, the period, he found that t squared proportional to r. This person is earlier than Newton. So Newton depended on his results and deduced that n must be equal to exactly, which came out with this idea that actually is inverse square. Very important equation. Though it is not true, in all situations, in extreme gravitational situations, that's when Albert Einstein comes. But in most of the situations, this is true. And where do you...
Yeah, why is this similar to the
You have to ask the person who created this law. Why is it that fundamentally, why is it that electric, the weirdest question is that why is it electric force and gravitational force is similar, but then why is magnetic force different? I don't know whether teachers have taught you this, but I'm going to say something that is quite about this one. Actually, magnetic field don't really exist. It's not don't really exist. It's magnetic field is come to the point of time. If I have time, I'll share with you that actually magnetic field don't exist.
So what about the iron filling? How about the iron filling thing that you see?
It is actually a relativistic effect of electric field getting distorted. Think of this. When do you have magnetic field? You must always have moving charges, right? Even for metal, for magnet, it's actually because of the spinning of the electrons inside. If you have current, moving charges. If you have solenoid, moving charges. You must always have moving charges. So it's actually an effect of moving charges. And how do we understand this effect of moving charges on moving charges? We call it magnetic field. Okay, this. I hope I'm not trying to answer you by confusing you.
So K is 1.
K is basically G times N. It is called the universal gravitational constant. It's 6.67 times 10 to the power minus 11.
And how do you get this?
Okay. What this person in Cambridge University did was that this person called Cavendish. It's just the laboratory name after him, Mark Cavendish. So what he did was that he hung a big mass, and then he hung two smaller masses over here. And he knows the distance from the center to center. So what he did was that he knew the string that hang these two things over here. Sorry, hold on. It should be this. And then these are two masses that are held on the ground. So these two masses over there is hanging on the rod that is held by a string. Now, do you agree that the amount of turn of the string actually creates some torque that tries to return the thing back? When you try to twist a string, the string tries to twist back. So the torque, the returning torque of the string depends on the angle that you twist. Yeah? So therefore, when he rests it in a neutral position, he finds that these two masses, due to the forces of attraction, pull each other towards a new position. So this will be the new position.
There are magnets?
No magnets, ball, just masses.
Just
Gravitational, just pure gravitational force.
Then that's heavy balls.
Very heavy balls. But you don't need heavy balls. All you need is, because this thing over here is a very small effect. That means the small twist over here creates a very small,
Very small track.
very small attraction. Yes, right. So what happens is that by knowing the angle that you twisted, you'll be able to find the restoring moment. Because the string, the properties of the string is something that you can handle. So therefore, the returning moment, which is equal to the force of attraction times the length of the rod, which is here, must be equal to the constant that which you know times the theta by which you twisted.
Yeah.
So it's horizontal.
Horizontal plane. Horizontal plane. That means two balls over here, another two small balls over here. So the string, because of the gravitational force, it gets attracted.
Yeah.
Then you twist the string up to a certain point where the restoring moment is large enough to stop it from moving further. Get it?
How does it get easy?
Then how does he know it's linear? Because this equation is linear.
No, it's
Right?
okay. That's the property of the string. Then you choose the string that is linear.
Okay,
That you have a choice.
okay.
That you have a choice.
Okay.
Yeah, that you have a choice. Yeah. Okay, let's rewind now. Okay. Basically, there are two balls over here. So just imagine this is one ball, this is another ball. Okay, horizontal plane now. Then I hang on a string a rod connected to two smaller balls. Can you see that this ball will be attracted by this ball? This ball will be attracted by that ball. So it twists the string, this string a little bit. Now that amount of moment is due to the gravitational force times the distance, which is the length of the rod, because this will be a force, this will be a force.
In moment.
Yeah, this is moment basically. Equals to the restoring moment provided by the string, because it tries to twist its angle. Right? Okay. So this can be measured, this should be done in another experiment, can be measured as well. So F over here, you know that it's G, big mass over here, small mass over here, this both can be measured.
Yeah.
Distance over here is this distance over here.
Sir. Then this is head through toe, toe through head. R squared, how did you get that?
No, R is just the separation between the ball and this one.
Yeah, but R squared, the power is 2, right? The 2 is...
No, I'm not proving this equation, I'm finding this constant over here now.
Yeah, but we use that to prove this.
No, this
Now
has
we're
been,
using this to prove that.
this has been proven, the form of the equation has been proven. This experiment, the objective is to measure this thing. It's not to prove the form of the equation.
Okay.
Yeah. Form of the equation has been proven within that already.
Yeah.
So therefore, by taking all the measurements, eventually you can measure this. Now why is this thing so important? Other than knowing the constant, because of this, you can actually measure the mass of the Earth. Why? The acceleration of free fall, this is actually the acceleration of free fall is 9.81. If you know this constant, the radius of Earth was known at that point of time, so if you actually know this constant, you know the mass of Earth. So this experiment that was done by Cavendish a couple hundred years before, it's actually called weighing the Earth experiment. It wasn't called the experiment to find G. It was actually called the experiment to weigh the Earth. Because once you can find G, you know the mass of Earth.
Sir, what's the unit of this constant? It's
Okay, you can actually work backwards. This is force Newton per kg. So if you work it back, it will be Newton per kg squared meter squared. Please go and find out more. Go and Google Cavendish, the Rocket Cavendish experiment. Cavendish. Experiment. Weighing the Earth experiment.
So see that people get dumb over it.
Sorry?
See that people get dumb over it.
No, not that people get dumb over it. It's just that people in the past they don't have the resources, so they get more innovative in solving problems. Over now, I mean, whenever you face problem, just amplify everything. Your problem is app. App. Just too singular, I think. That's the irony, right? Because of the lack of resources, you get more innovative. Because of the abundance of resources, you get less and less innovative.
So,
Yeah.
is the G, okay. Is it the constant G, is it
The
the
big G over here.
constant for like
All masses.
gravitational
It's
attraction?
universal gravitational constant. It's the same here, it's the same 10 million light years away.
Okay, so it's
That's what we understand now. It may be different now. Okay. Cool. It's like, whoa, kaboom. Okay, this marks the end of the advanced computer. Stop the video here, then I'll reload another video. So that there's a clear cut.